Well, welcome back, everyone. So far, we're nearly there. This is not an easy day to attend, so I appreciate people being here, whether you're here on Zoom or in person. Well, it's official, folks. This is now the last day of the last instructional week of the whole semester. Congratulations on making it here. After today's class, although is going to be left on the table for us is to get through the final exam. The information is provided down below that we've rehashed before. It'll be from 8 to 10 p.m. for the in-person section or 5:30, 7:30 p.m. If you want the earlier time slot, I'll be here for both. And for the online section, make the arrangements with the Pocatello, Idaho Falls, or otherwise testing center as usual, and you'll be all set. If you have any questions on getting that scheduled, particularly in the online section, don't hesitate to reach out. I'll make sure we get that figured out right away. But any questions at all, folks, before we jump back to this problem set here? Okay, well, our goal is just to do as many problems as possible. Any problem that we don't solve on here, I'll have the full solutions posted later on, and I should get them up pretty quickly, probably on Friday. And here's where we left off. A plotting problem out of nowhere, but this is our transition from dealing with differential equations, sections 9395, now into chapter 11. The notes are kind of sporadic from here, but for the moment, this is going to be a good amount of chapter 11 type of problems. And if at any point we're solving these, you'd like another problem looked at, don't hesitate to interject. Otherwise, we're just going to kind of go down the line on these problems here. So starting off, problem number 7, we're looking into a sequence going from 1 to infinity on terms defined to be cosine n pi. We want to know why the limit does not exist. So in other words, jumping to part B, we're going to say limit n goes to infinity of an defined to be the limit as n goes to infinity of cosine n pi does not exist, and we need an explanation. You might already have that explanation, but let's do the plot next, and it's going to reveal it. So we'll come back to this part. Plotting the first 5 terms of the sequence is a plot that's really focusing on quadrants 1, quadrants 4. Since we're going to begin at n equals 1, so here are the values 1, 2, 3, 4, 5, kind of with a little bit excited on the length of that, but that's all right. As far as cosine pi goes, it's going to be between positive 1 and negative 1. And now we're just plotting values. Throw in the index 1, it'll say that a1 is cosine pi. But cosine pi itself is down at negative 1. And that gets our first term of the sequence plotted on the axis. And next value, a2, this is going to be equal to cosine 2 pi, which takes us up to now positive 1. So we're at index 2, move over 1 tick mark, and we're up here. And already you probably see the pattern. A3 is cosine 3 pi, which is exactly the same as cosine pi. These are a 2 pi periodic function. So just subtract 2 pi from there. We're back to cosine pi, back to negative 1. And so we're down there. This establishes the pattern for every single one of these terms. We're just oscillating from negative 1 to positive 1 to negative 1 and so on. And this pattern just continues forever. In order for the limit to actually exist, these dots have to be getting closer to each other. That could be forced to happen with the right thing in front of cosine. But as it's written, we'll say it does not exist because the terms of the sequence never approach any number. it never settles down to, say, a limit of +1, 0, or otherwise. We're always just separate out in those terms. Well, that's our first problem of the day, kind of a quick one, just a really more of a concept kind of question more than anything. Any questions at all, folks, on this one? Okay, we know chapter 11 gets kind of exciting after a while, so this is just a kind of a warm up to what we're dealing with. The sequences are just the terms. And if we're talking about series, these things down here, now we're adding up all these terms and trying to decide, does the total sum exist? If it's a geometric series, we might even be able to use a formula to say what the total sum equals. But these problems are fundamentally, first, does it converge or does it diverge? And just like on exam 3, if the integral test comes up, I'll often indicate it this way. Use the integral test. That way you know that this is the problem where you want to use it on. These are pretty fast problems, but it's kind of like the improper series type 2 problem. It's really touchy just on the setup. So first thing we want to do is define a new function. Let f of x be defined to be natural log x divided by x on domain. We let the indexing down here tell us what the domain should be. It's weird that it starts at 2, but it couldn't start at 0, right? That's division by 0. It could start at 1, but natural log 1 is 0, so that's an uninteresting term. So we're just starting it on 2 on this one. That's going to give us the first non-zero term. So we go here and say it's domain 2 to infinity. So thoughts about this function is that the natural logarithm of this is positive on 2 to infinity, and definitely so is x. So we can say then f is positive. We can also say continuous because we skipped across the discontinuities. And the natural logarithm grows exceptionally slow, much slower than the linear function. And so we can conclude and decreasing. And this is all valid on 2 to infinity. Let's just squeeze it in right there. That means the integral test really does apply, but I mean, if you're told to use the integral test, it should apply, or else the whole problem is flawed and would have to be thrown out. But it's good to just think about this. You don't necessarily have to write it down as a step, but those are the conditions that had to pass. Then when all this qualifies, we're going to take this function to an improper integral that goes integrate 2 to infinity f of x dx. Like the last problems, we do have to write in the limit, send in the direction instead of x. This is a new variable t going in the direction of positive infinity. And the role of t is to wipe out that infinity and put in a finite number. That's the only way we can actually use the fundamental theorem, part 2. So we're integrating from 2 to infinity. And this would be the required setup step for the full credit on this kind of problem. Throw in the integrand, it's natural log x over x, dx. And now we just need a quick u substitution to run through this problem right here as it stands. Usually, natural log x gives us a pretty good dead giveaway on what a good u can be. If u is natural log x, then differential du would then be 1 over x dx. So we can substitute out these values here. Next, up to you how you'd like to handle the limits of integration. I'll swap them out and say they were x equals t, x equals 2, so from 2 to t. Now I'll just throw them inside these positions. They're going to convert over to natural log t, natural log 2, and we've done a lot of analysis on that limit. It's now ready to go. It's a new limit as t goes to infinity from natural log 2 up to natural log t using the limits of integration on the right. Following u substitution, this becomes a u du. So the integration here is usually very straightforward for improper 1, improper 2 on a final exam, because the major concept is getting through the improper integral, which is the whole concept of the integral test. So next step, antiderivative is immediate, a half u squared. So we have a half limit t to infinity of u squared, evaluate from natural log 2 to natural log t. Now at this stage, we use the integral test, but we might have used a comparison test in just a nice right kind of way to show the same kind of conclusion. This looks like it's going to be automatic divergence when we go to take the limit, much like the harmonic series would have been. So this is now a half. The limit's still alive as t goes to infinity. Like we mentioned last class, with any improper integral, you definitely want to show this next step just to get some clarity on the limiting phase. This is going to be natural log t squared minus natural log 2 squared. I don't like those parentheses. We can make that a little bit easier to read with a bracket, I think. But now this is going to resolve the whole limit right here. As t goes to infinity, natural log t does. And so this whole thing is now infinity because of that part right there. That means the improper integral that we wrote down diverges. And then that finally means by the integral test, our original sequence, let's give it a name, summation an, we'll say therefore summation an must also diverge. And at that step, we did it, folks. That's the entire test. The integral test is not too bad, but sometimes if the integral is kind of built up, it can be like almost torture. We did some pretty hard ones on the homework exercise, ones where there were partial fraction decompositions. But on a final exam, it's going to be kind of more routine like this one. Any questions at all, folks, running through that first one? Okay, now down the list. Looks like we're still in chapter 11. This would be more section 11.2. It is an interesting concept question, but it's one of those important concept questions where we're trying to figure out what exactly is the difference between a sequence and a series. Problem number 9 is challenging, but it's helpful in that sense. And that's a big deal in the final exam. If we ever get mixed up between sequence and series, we are possibly giving a totally wrong conclusion of convergence versus divergence. So here's how problem number 9 is going to help. It says for the sequence an, summing from n equals 1 to infinity, it is known that this associated sequence Sn converges to 1. What we're saying here, if it converges to 1, is that the limit as n goes to infinity of Sn is 1 as a sequence. But this is not an ordinary sequence. This is the sequence of partial sums. So what it's doing is gathering the first n terms for Sn and just adding them all together from the original sequence. So this is what makes series a little hard in a certain sense. There's the sequence. There's the sequence of partial sums. Then there's this series, and all three are on paper at once when you're talking about series, any series whatsoever. So lots of moving different parts. Now, we have a limit equals 1 for the associated sequence of partial sums. We want to know, does the series now converge? The only difference between the series and Sn over here is that it's always a finite sum. N tells you the number of terms. But the series, we go off to infinity on this one. And that's what the dot, dot, dot is saying, infinitely many terms that we're taking. Again, this is just a concept question. To determine convergence or divergence here, there is no test. This is by definition. We'll say, by definition of a converging series, as defined in section 11.2, summation as n goes from 1 to infinity, an is now the limit as n goes to infinity of Sn, the sequence of partial sums, provided this limit actually exists. But we were told it converges to one. We have to now put that together, meaning the limit exists and it also equals one. So that means this limit equals one. And because the limit exists, the series down over here converges. Let's say here just briefly, this shows summation an, written more briefly just as a symbol now, converges. Well, does that make sense to folks on part A, how the sequence relates to partial sums and then relates to convergence? Awesome. How about for part B then? Now we're talking about the original thing from the very beginning, that sequence. It's involved in the partial sums, it's involved in the series, that's where all the terms are being defined for each one of those things. We want to know if it converges or diverges. Any volunteers for the conclusion on this one? Kind of a tricky problem in a certain sense, but here's a thought. What if it diverged? That might mean the limit doesn't exist, or it might mean the limit is 2, or it might mean the limit is infinity. But what would those things mean? Let's take the one where the limit is 2. That means as you add more and more terms to this sum, which is an infinite sum, the terms you're adding infinitely together repeatedly are getting closer to add 2, add 2, add 2, if the limit converged to 2. In fact, another theorem in section 11.2 told us that since the summation an, the series converges, it immediately, for every convergent series, follows that the limit as n goes to infinity of an, it is a specific value. Good call, it's got to be exactly 0. So that tells us it converges, and it tells us even more, it's converging to 0. That's essentially what the test for divergence was all about. If we take the contrapositive of this whole statement here, we'd say if the limit is not 0 or does not exist, this does not converge, i.e. diverges. This is just the same statement in a different order, relayed through by the contrapositive of them. So since an converges, it follows that the limit is 0. We didn't answer this yet, so let's put it down here on paper. So an, just writing it out as a sequence, converges. So that's our relationship between what we're dealing with the series, think infinitely many terms, defined by the limit of finite terms as that number goes larger and larger. And convergence here implies the sequence itself has to converge all at once. That's a lot of thoughts to stitch together, but any questions at all, folks, running through this material? Okay, so aside from this concept question right here, let's take a look at what other series and sequences we can get into. Well, this one's definitely a series, and you want to test this for convergence, divergence. It's just a mess. Definitely, I wouldn't use the integral test on this thing. It looks like it's a nightmare. I think a good test for this, well, not test for divergence because of the relationship between numerator and denominator. The limit on this thing is 0, unhelpful for us. We cannot reverse the logic here. If the limit is 0, and that's what we start with, we can't reverse back and say converges up here. But you know what would work really well for this would be the limit, comparison, test. Which means we have to test 2 series, but that's okay. It's not too bad to get through these. Call that summation an. That's the one we ultimately want to test. But to do that, we define a new one, summation bn. The way we grab it is we take, when n is very large, the most important term, and I want really just the variable part, rather not the coefficient 3. So we're going to grab the n squared, most important part in the numerator, divide by n power 4. Double check that order isn't bad, where it goes n power 4, n power 5, or something like that. You're taking the highest degree term here. Then bn is going to be defined as a sum from 1 to infinity of that n squared divided by n power 4. We need to reduce this and then test it. This is 1 over n squared, which is a great series to test, right? This is one of the fastest tests we have. It's faster than the test by divergence. We just say what it is. It's a p-series. That automatically means you're using the p-series test. So you can either say that or p-series test. You have to tell me what the power is, so I know that you know what the power is going to be on this. It's at power 2, and this is the condition for convergence, greater than 1. We have to say what this conclusion is, so we just say converges. So that's half of the limit comparison test. The other half is to do the limit itself. So let's run through those steps. We'll take the limit, n goes to infinity, of an divided by bn. So now it's the limit as n goes to infinity of all of this stuff, 3n squared minus 5n plus 4, 2n power 4 plus n minus 8. Divide by bn means multiply by this as a reciprocal. Really, the most work you do on this limit is just writing all this stuff down on paper. So multiplying through, it is now 3n power 4 minus 5n cubed plus 4n squared. So denominator set up, or numerator, and the denominator is exactly the same. 2n power 4 plus n minus 8. And this shows up so often in this class. That's why we mention this strategy. If you have a tie in degree numerator and denominator, all you're doing is grabbing coefficients and your limit is done. So this limit is 3/2. That's what we want to see in limit comparison test to get the right conclusion of either both converges or both diverges. We want finite and we want greater than 0. So this is the condition the test works. It's not telling us convergence or divergence. Convergence or divergence came from right here, the one we compared it against. So once we have that conclusion here, we can say, therefore, summation an must also import the same exact statement you said here, and you're always going to be correct. If you said diverges, you have a positive limit that's finite, you'd say diverges. Because we said converges, we'll just say it again. Must also converge. And just to tie those together, an arrow never hurts. So here's the arrow. If the limit comes out this way, the fates of both series at once has to be exactly the same as the thought with limit comparison test. Well, it's a tough test because, again, there's actually a lot to do. You have to do 2 tests at once. This might not be a p-series necessarily. Then you have to run through a limit, and the conclusion itself is tricky as well. Any questions on any elements of this one? Okay, so we survived a limit comparison test and integral test. Let's see what's next. This one's nice. Anyone happen to see the method on this one? I would say this is the giveaway right here if you're not sure. That part right there is going to alternate between +1. Let me check that out. Yeah, first term is positive. There'll be -1, +1 again. If it's alternating, then that's the giveaway. Use the alternating series test. Yellow highlighting just to say that's the element that caused us to want to use that test. And the test is interesting in the sense that the major element of this test is analyzing a sequence now. So we go and let the sequence. This is an important thought here because when we go to write Bn, a mistake is trying to test it as if it was a series. That's a common mistake to make here. So let the sequence Bn, as n goes from 1 to infinity, be 1 over root n, as n goes from 1 to infinity. Indexing here is helpful because it's telling us that this is always positive. But by the format of this, as we go up to infinity, it's also telling us Bn is decreasing. We're bound in the numerator, denominator would go off to infinity as n goes to infinity. So this just gets smaller and smaller for larger and larger values n. Then at the same time, really using the prior conclusion, we can say the limit as we go to infinity of Bn, as a sequence, the limit as we go to infinity of 1 over root n, this has a limit of exactly 0. It's not only just decreasing, it's decreasing down to 0 in the limit. So we'll say here, our work is done. That's all we have to show here. Oh, hang on. Let's take a look at the instructions, however. We want to determine if it converges absolutely, conditionally, or diverges. You know, this is an important test strategy as well. Read the instructions. It was nice to see it's an alternating series, and we do have to do this work to show convergence, but that's not the whole problem. Let's wind back that fancy-looking conclusion and just make a smaller conclusion. This shows summation an converges. But it doesn't resolve the question because now all we've eliminated is the potentiality for it to diverge. We want to know if it converges absolutely or if the convergence is a weaker form, conditional. That means we go back to an and we look into this. So next, test summation absolute value an. This is a whole different series. Well, it's based on the original one, but it is not the same. If it converges here, it may converge here or diverge. That's what we're going to take a look into next. It's a summation from 1 to infinity. Absolute value, -1 power n minus 1 over root n. So we're not taking the absolute value of the whole series. That's a whole different expression. We're taking the absolute value of all the terms as we add them together one by one by one. All the terms are now going to be of this form, 1 over root n after taking the absolute value. So that part that became alternating, either positive or negative, is gone through absolute value. And let's rewrite this even more suggestively. This is a sum from 1 to infinity of 1 over n to power 1/2. Showing that power is a pretty big deal, I'd say, because now it reminds you this series, even though it's fancy, it's built up from the original one, it's still something familiar. It's a p-series. The power p is 1/2. Let's write the condition for divergence, which is less than or equal to 1. So it diverges. Let's say what diverges, since we have something like 2 series and a sequence on the paper now. Summation absolute value an diverges is a better targeted conclusion now. At this point, we've resolved the problem. We just need to state a conclusion. It does not converge absolutely, because when we took absolute value of terms, we've got divergence. It can diverge because we showed it converges. So here's our big conclusion. Now is a good time to write down, therefore, to wrap this up. This shows that the original series, summation an, is conditionally convergent. But pretty interesting rundown on these different kind of methods. Any last questions, folks, on getting through this one? Okay, so that was problem number 11. This is like midway through chapter 11 rather, already at this point. And now in this problem, we're getting into some of the bigger tests. the radius and interval convergence of the power series right here, or rather, it's not quite just a test. This is a whole function. And if we want the radius and interval convergence, what we're asking for is the domain of this function expressed in a couple different ways. So now let's call this f of x. This is a section 11.8 problem. The very first step for a problem like this one is just hit it with the ratio test. The ratio test fails on a whole lot of problems. For example, you would never want to use a ratio test on this one. The limit isn't going to come out as anything other than a 1. Ratio test is going to be terrible on this, and again, the limit's just 1. Even if you successfully navigate through that limit, and it's a nasty one, you want to use ratio tests when you have things like this. X on the inside, or maybe factorials, other kinds of oddities are the best situation for that form of test. So let's begin by ratio test as we indicated. In that ratio test, we want to look into the n+1 term, and that means we're just going everywhere inside here, incrementing n by n+1. So this will become -1 power of n, x plus 2 power of n+1. Down below, n+1 times 2 power of n+1. Then do any kind of simplification you might need on here. Definitely if there's factorials, it's probably a good call. Otherwise, if you feel like we're in good shape on this, let's call this whole thing summation an and write out the limit as n goes to infinity. In ratio test, it's always the next term, an+1, divide by the nth term, an. Next thing we have to do is very carefully write out this. This is really the major step right on this line right here. First, I'm going to throw in this stuff, do a slight amount of factoring. -1 power of n, x plus 2 factored, leaving x plus 2 power of n. I'm going to leave n+1 as it is, but let's factor that too. 2 times n+1 times 2 power of n. And that takes care of an+1. Biggest danger about this, like we mentioned, is there's lots of factors. So just make sure you carry in all the stuff in both spots. And when you cancel, you don't leave anything behind. Dividing by an is going to give us n, 2 power of n in the numerator, -1 power n minus 1, x plus 2 power of n. If you go very carefully, methodically with this, you're going to be on the right track because here's all the cancellations next. The exponential function is just gone. Here's the exponential function base x plus 2, also eliminated. Through the absolute value portion, you can cancel your negative signs right here if you'd like. Now we don't have to worry about them. And left behind, x plus 2, n plus 1, and a 2. Here's our next step to write. This is equal to the absolute value of x plus 2 coming from this position, divide by 2. Those things are constants relative to the limit as n goes to infinity. Because it's a limit on n, anything involving n still is now trapped inside the limited expression. So n divided by n+1 looks like it's all that remains, these two portions. Let's double check. Everything got selected here. That again is easy to make a small mistake on this. I think we've got it. Now we just need to do the limit. It's 1. So now the limit is done. We get the result. X plus 2 divided by 2 times 1. Times 1 came from doing the limit. And now we write down the condition for absolute convergence of the ratio test. Ratio test gives us absolute convergence when it's strictly less than 1. In absolute value, which is what we calculated, this is what it solidifies to. And so we have x plus 2 less than 2. And already this is giving us the radius. Let me write that slightly better. The radius of convergence is now 2 by this test. The next thing we need, we've got this down, is the interval of convergence. And in this problem, because the radius came out finite, in this section, we often call this case 3, which meant we must test the boundary since R is 2. If it was 0, then it's only going to converge right at that point 0. We don't test the boundary. I mean, 0 is, in a sense, a boundary at that stage. If it was infinity, there's no boundary either. It's just converging on the whole real number line. So whenever this happens, if you get a finite radius greater than 0, we test the boundary values. That's sometimes kind of vague, so let's do this really carefully. Any questions at the moment? Okay, maybe a good way is sometimes it just helps to have a picture. Anything to make this a little bit more concrete is a good strategy. The center of this series is centered right at -2. It's the value plug in for x to get 0 as the total sum. Or you can observe from right here, it's the value that will give us 0 here. We want x plus 2 less than 2, and the center is at -2. Another way to look at this is that this is -2 less than x plus 2 less than +2. Add to 2 both sides, and 0 less than x less than 4. Yeah, that's looking weird to me. Yeah. Subtract 2, thanks for that one. So subtract 2 from both sides to get the right result. We'll get a -4 less x less 0. Thanks for spotting that weird subtraction on that one. So that looks a little bit better on this one. Or you could have just said, if the radius is 2, go 2 units to the right to 0. That's another way to do it. And 2 units to the left to -4. So here's our -4 to 0, either way we see it. Now, it's an open question if it converges here. So I'm going to put in a circle. I might leave it open or I'll fill it in. But everything on the inside is absolute convergence. So we converge on this interval. The only question is the boundary. So that's where the further testing is going to occur, at -4 and at 0. Let's bring this back in. Well, we're done with the test. Now we have a radius. We're interested in the boundary values. So here's what we say next. Let x be -4. Now let's take a look into this. If x was -4 here, this would be exactly 1, and we wouldn't have any conclusion. The ratio test failed right at exactly 1. That's the whole reason we're doing this. If we plug a 0 here, this whole thing is exactly 1, and the ratio test fails once again. This is always a failure on the boundary for the ratio test, not the other test, like the geometric series. So that means we're taking x equals 4, writing down summation an equals a sum from 1 to infinity of -1 power n minus 1. And here's the substitution. If x is -4, we drop it in right there. -4 plus 2 in that spot to power of n. Divide by n power times 2 power of n. Now we just need to do some work on this and say, what is going on with this whole series? So a little bit of algebra is going to give us a sum from 1 to infinity, -1 power n minus 1. This is now a -2 power of n. Down below, we have n 2 power of n. And this cancellation is kind of involved out of nowhere. Let's take our extra time with this one again. Let's factor this so we cancel cleanly. This is a sum from 1 to infinity, -1 power n minus 1. And where the red dot is, that's really just -1 times 2 to power of n. So we can rewrite it -1 power of n times 2 power of n, divide by n times 2 power of n. This is where the cancellation actually occurs, 2 power of n, but it leaves behind two alternating terms. That's kind of annoying in a way. Let's be really, really careful with this. This is more confusing than a real exam question could be, but it's still a good concept. You take -1 power n minus 1, multiply against -1 power of n, you can add the exponents, the bases are like, and this becomes 2n minus 1. Now think back to what we did with power series. This is always odd. No matter what index you put in for n, we've got an odd value, and -1 to an odd integer power is -1. Kind of curious, right? If you take two alternating terms multiplied like this, we've eliminated the alternating possibility of it entirely. It's force -1 always, but I think that's pretty hard to see. It's good to be careful with this one and just write it out like that. Because it's a -1, we can even move it in front of the sum and say n goes from 1 to infinity. Here's the -1, so it's not a distraction when we determine convergence divergence. And all that's left is 1 over n. We have -1 times a divergent harmonic series, still diverges no matter what constant we multiply it other than 0. So let's say here, this is the divergent harmonic series. It was just extremely well disguised right in this step. It took some algebra to really see it. Does that make sense to everyone in getting that conclusion there? Okay, again, this is also a good reminder. If summation 1 over n, no matter if you're multiplying by a constant like this, if this ever occurs, you don't have to test it. Just say the name and the conclusion. So that means we leave this open at -4. We don't have any convergence there. Now we're wondering what happens at 0 next. So another boundary value. Interesting things always happen on the boundaries for these things. We'll say let x be 0, come back down to the original series and just throw 0 right up in here for x, and we'll have n goes from 1 to infinity, -1 power n minus 1. Here's the 0 for x plus 2. This one looks a little bit nicer to get through, a little bit more straightforward. We're dividing by n. Oh, don't forget the n is there, as I did, times 2 power of n. So this is a sum from 1 to infinity. It's alternating. We have 2 power of n divided by n times 2 power of n. So no trickery here with the exponents. That part's just gone. One more step just for the sake of clarity on it. One thought you might have had about this series, though, is this is called the alternating harmonic series. Whether it starts at -1 power of n, +1, -1, we still call it the same thing, an alternating harmonic series. So it's telling us it's not necessarily unique. Depends on whether it's starting at a positive or negative term. But in either case, we call it alternating, and it's known to converge. So let's say it here. This is the alternating harmonic series, which converges. And we're running out of paper, so let's say it continues. But back up to the top, what we found is convergence on the boundary value right here, and diverges on that boundary. So our work is done. We just need to simplify, or not really simplify, but paraphrase our results. We'll say here, therefore, the radius we found to be 2. Even if we forgot what it was, it's a distance to 2 from the center to the boundary, so that implies radius 2. And our interval of convergence is open at -4, and it goes up to 0 with a bracket. So the whole thing is done. We now have the domain of this weird function down below. Well, any questions, folks, with the review of those methods? Actually feels like it's kind of been a while since this section. Okay, so this was two problems like this on the last exam. One problem was like this one where R was 2, not as much weird stuff with the exponent. But another problem is if R is infinity, or excuse me, if the limit here came out as, say, infinity, R would have been 0, and I would have just been the center, -2. If this came out as exactly 0 right here, it would wipe out the x plus 2. Then R is infinity, I is -1, or excuse me, from negative infinity to positive infinity. So this is the tougher case to get through, but makes it a good one to review on the final exam review. And now here's our next one to take a look into. Construct the Maclaurin series representation or tangent inverse x, state interval of convergence. The hint here is major, actually. You don't have to do it this way. You can use the definition of a Maclaurin series if you prefer, but this hint reminds us that this is really a section 11.9 problem. And the section 11.9 problem, here's the tool we used. The geometric series can be expressed in a lot of different ways. If we're testing an ordinary series, like in sections 11.2, we have it written in with a times r power n minus 1. But if we're thinking in terms of Maclaurin series, here is the geometric series as a Maclaurin. 1 over 1 minus x is a summation from 0 to infinity, x power of n, provided x in absolute value is less than 1. So this is the formula we're going to use to get through this one. The function is f of x equals tangent inverse. And let's take the hint and make the problem a little bit more manageable. F of x equals tangent inverse of x implies f prime at x equals 1 over 1 plus x squared. So we've got our derivative down. Now we're just matching up the format. We already have 1's in the right position. We just need double negation here to get the minus some expression for x. And whatever we throw here just gets raised to an nth power. So let's rewrite f prime at x. 1 over 1 minus negative x squared. So now it's in a sum from 0 to infinity, negative x squared power n. So we just took whatever is here, dropped it to that position, maintaining the same structure for the geometric series. Now we have to bring this back through integrating to get to the original function f of x. So let's take some extra steps here and write this as sum from 0 to infinity, negative 1 power of n, x power 2n. Also, the series for f of x could be more involved than this series, and this series is way easier to test. We just use that to get its, let's see, interval of convergence in one shot. And that interval of convergence can carry over to the next part. Actually, hang on, that's not necessarily true. These instructions are a little bit tough. If I'm going to use this, it's giving me a radius of convergence. But when I go to integrate, the radius won't change, but the interval might. I think a better version of this problem, let me rewrite it, would look like this. The way we actually did this problem in section 11.9, let's make it more familiar so we're not taking loads of extra steps, is state the radius of convergence. The radius of convergence won't change if we differentiate and integrate. So if you find the radius of convergence through here, we'll have it when we wind back f prime of x to ordinary f of x. So sorry for that quick edit on that one, but this is the way we actually did the problem in that section. So we're matching up our methods at least. And also not taking a whole lot of extra time on this one problem. Next thing we'll do is, to get this statement, we'll say provided in absolute value, this thing, negative x squared, is less than 1, But we know solving these is usually not too big of a deal. This whole thing becomes x squared less than 1. Then we take the square root of both sides of this inequality, and we're back to absolute value of x less than 1. So no different on this one. If we had, say, divide by 4 or something like that, this would change a good amount. But what it's now telling us is radius of convergence on this is 1. Well, we're on the right track. Now, the next thing we're going to do is get back to tangent inverse x by writing in tangent inverse at x is going to be the integral of f prime at x, or hang on, let me write this in a slightly better way. So tangent inverse x is originally f of x. But I want to tie f of x to f of x is always the antiderivative of f prime of x. The only downside with this kind of formula is we have to solve for the constant on this one because we don't want a family of functions. We want the one function that's going to come out correct. So put in position f prime of x, that whole Maclaurin series right here, and we'll get tangent inverse x equals integrate the sum from 0 to infinity, negative 1 power of n, x power 2n, dx. And we're just about there. We now know that tangent inverse x equals, take the antiderivative and we get the constant c of integration. Kind of annoying step, but this is a fast one to solve c on. Plus another sum from 0 to infinity. This one stays exactly the same as a constant. Integrating this part gives us x power 2n plus 1 over 2n plus 1. That's an x there. Let me fix that. Radius of convergence is still r equals 1. So we now have a Maclaurin series. The only thing we need to determine is what is that coefficient c right there? Well, any questions so far, folks, to this stage? Okay. Well, the strategy is find the center. Center on this one is 0, so that means take this whole equation, set x to 0. X to 0 will then imply tangent inverse at 0 equals the constant plus, throwing 0 here is not a big step. The whole thing is now 0. It converges, and we can say the total sum, exactly 0. Then tangent inverse 0 is also 0, so the constant is 0 on this problem. I believe in a homework question we did, the constant came out as something different, but in class, looks like it always came out 0. Sorry about that. Probably should try to look for some more variety to bring. But usually these go pretty fast either way. And now we have determined tangent inverse x as a Maclaurin series, because the center is 0 and it is a power series, is a sum from 0 to infinity, negative 1 power of n, x power 2n plus 1 over 2n plus 1. And because we changed the exercises in a major way, we're not going for interval convergence, which would require us to test at the boundaries potentially. Here, we'll just import radius is 1. That's the thing that will not change when we integrate like we did here or differentiate. Well, any last questions, folks? Kind of an unusual question because we called it a Maclaurin series. Okay, so this was our section 11.9 problem. And as far as the exam goes, you don't have to follow the hints, but oftentimes it's usually going to be the faster, more direct method to get through the problem. So let's try out to the next one then. This one was a Maclaurin series, but it felt like a cop-out because we just got there through the geometric series. This one's different though. We're dealing with f of x equals natural log x, centered at a equals 4, using the definition of a Taylor series. But I think we did something similar to that. Let me just double check. I think we did that same exact problem, actually. F of x, we did as a Taylor series at center a equals 4. So maybe let's change this one up to say, just for the sake of a little bit more variety, how about e power 5x? A little bit different. Is that okay with folks on this one? Okay, I hadn't noticed until now that, that seems really familiar. This is the strategy if it's natural log x. It's kind of unusual one because it has one term that didn't fit in. And you do a lot of work sorting out the coefficient. Let's try it again with something new and different. This will be not as complicated, but it makes it more of a difficulty level for a kind of problem you see on a real final exam. Here's the process of this. If you see a Taylor series problem, it says by the definition of a Taylor series, you probably have a completely blank page and just the problem, because there's a lot of scratch work to do on this kind of thing. Start off with a 2-column system. F of x is e power 5x, and then do f at the center. Center we set to 4. So that's going to be e power 20. Now we start differentiating with the goal of trying to find some pattern here. So differentiate. Mind the chain rule. That's a silly mistake to make on these kind of problems. This is going to be 5 times e power 5x. Then over here, analyze it or evaluate it rather at the center. F prime at 4 is now 5 times e power 20. And because every time we differentiate, we get e power 5x, it looks like e power 20 is a big feature of this problem right here. Here's second derivative. Chain rule again is going to give us 5 times 5, so 5 squared, e power 5x. So second derivative at the center 4 is 5 squared, e power 20 again. Already, you probably already see the pattern. Each time we do a higher order derivative, we just get a higher order exponent on 5. Let's write it down one more time just to emphasize. Third order derivative at x is through the chain rule, 5 cubed, e power 5x. Evaluate it at the center 4. We get 5 cubed, e power 20. So let's see if we can really see the pattern. Third order derivative gets power 3. Second order is at power 2. First order, just to emphasize, here it is at power 1. And f at 4 is really f power 0 times e power 20. The pattern carries down all the way down the line, starting at index 0, 1, 2, and so on. So now we make the really big conjecture that Fn at 4 is nothing but 5 power of n e power 20. So that's our pattern. It then tells us the coefficient we'll use in the power series defined as Cn, which is equal to Fn at the center divided by n factorial is equal to 5 power of n e power 20 divided by n factorial. Once you get Cn, you essentially have the entire Taylor series. The original function was e power 5x. And now we have this wild representation. It can be re-expressed as a sum starting at this index, which fit the pattern cleanly, going from 0 up to infinity. Throw in coefficient, 5 power of n, e power 20 divided by n factorial, and then multiply it by x. Here's where we have to be careful, minus the center, raised to power n. We've got it, folks. This is our representation. We need to determine the radius of convergence. But if there's a factorial there, it's probably R infinity for radius. We're going to check it out by the limit, or excuse me, the ratio test once more. But any questions at all getting to this step? Okay, this is the major work on this kind of problem. Now, last thing we have to do to finalize the problem is check this part out, see if the radius really is infinity. I'm going to put a box here just to convey this is where the answer will be, but my work is now below. It's always kind of unfortunate. Usually you want your answer at the end of the work so it flows right. But this is a weird problem, so it just flows weird as well. Now, let's call our method here ratio test, where we will take the limit n goes to infinity, an plus 1 divided by an. Let's write that in. Well, you know what? We might want to be careful with that one. There's factorials involved. We'll be a little bit more accurate if we take our time and simplify what an plus 1 is. An plus 1 is going to be 5 power n plus 1. E power 20 is just kind of sitting around there as a coefficient. X minus 4 power of n plus 1 over n plus 1 factorial over here. So when we split this up, we get 5 times 5 power of n, e power 20, x minus 4 power of n. But the bigger factoring is just making sure nothing crazy happens with that factorial. Let's break this up as n plus 1, n factorial. Then using this is the numerator and the limit, or excuse me, the ratio test. So now it's a limit as we go to infinity of 5 by 5 power of n, e power 20, x minus 4 power of n, then n plus 1 factorial. We multiply by the reciprocal of this thing. So think of x minus 4 as attached to the numerator. When you take the reciprocal, sometimes it's kind of hard to visualize it in a weird sense. So it's just n factorial in the numerator, 5 power of n, e power 20, x minus 4 power n. Barely made it in on the page width, but now we get to cancel. N factorials are gone. The awkward e power 20 is out of there. All of the exponential powers, 5 power of n, x minus 4 power of n, eliminate as well. And not too much to say here. In fact, it doesn't even look like we did need absolute value for the x minus 4 rather. But that's the only thing that's going to settle on. It's now absolute value of x minus 4. So that term is a sole survivor in the numerator. I guess there's a 5 as well. Coming from that cancellation. And the limit goes, as n is off to infinity, 1 over n plus 1. But that's great, right? That's a limit of 0. So this becomes 5 absolute value x minus 4 times 0 from the limit, which is 0 less than 1 for all x and r. And that statement, the fact that we maintain the condition of convergence, and this works for all x, is what tells us radius is infinity on this one. If we wanted the interval of convergence, it wouldn't have been much work. We would just say from negative infinity to positive infinity. That's kind of a big problem, even though we shortened it up a little bit with e power 5x. Any questions at all, folks, on the process? Okay, we're at that part of the course where we need to make a judgment call. We've got about 2.5 minutes or 3 minutes so far. And next question looks like a concept question. I'm not sure if we can get too far on this one with the time we have. I'm not going to ask any kind of crazy concept questions like this one, but they're still pretty valuable to look into because the purpose of this kind of question is it's going to really clarify in your mind, how does the, say, alternating series test work? How does test for divergence work? All tie together with these interesting conditions and small changes that we make through here. So it's an interesting problem. I'll give the full solution on this one. This is the one that would be a potential extra credit question. This came from section 10.2. Looks like all I asked for you on this kind of problem was doing these two derivatives here. And, oh, follow-up question on which points are the tangent line vertical on this one. So this is just a way to say this one could be a potential extra credit question as well. And then as you get further and further through the document, it sort of just loops back. We're just rerunning back to chapter 8, doing some more kind of problems like these, centroid problem, and then a whole bunch of chapter 11 convergence, divergence problems. So really we got through the main set with where we're at right now. This might be a pretty good stopping point for us at this point. If you're looking into the further document, it's just more review problems, same kind of material. So any last questions at all, folks, if we're calling it a day right here? Okay, well, have a great weekend, folks. Have a great night. If you're doing any work over the weekend, don't hesitate to reach out if you have any questions or comments, things like that. Also, great strategy for studying for the final exam is not just looking at these problems we were just in. They're great problems, the final exam review problems, but also take a look into some of these documents. I'm going to post blank exams 1 through 3. They're great ones to take a look into. And the final due date for our homework, which is worth 30% of the course, is going to be the day of the exam, Monday, May 5th. So that tells some people this could be the optimal way to study. If you're behind on a couple assignments, this is probably the very first place you ought to start. But otherwise, have a great weekend, folks. I'll see you all on Monday. Yep, take care.